So then I'd like to welcome you to the last step in the PhD process of Kubilay Demir. And as usual, this meeting will have three phases. So we'll start with a lecture by you, which is roughly 30 minutes. Then there will be 1 hour of discussion, and then after that I will ask all the guests and also the candidate to leave the room, and then we will decide on the verdict. But with this, I hand over to you.
Hi everyone, welcome to my PhD defense. Thank you very much for being today here. I am Kubilay Demir from this group. The title of my thesis is A Secure and Reliable Communication Platform for the Smart Grid. I divided my presentation into 3 parts. In the first part, I will introduce the background and motivation of my thesis. After that, before giving the problem statement, I will introduce the smart grid communication requirement and challenge. In the second part, I will introduce my all contributions sequentially. In the third part, I will give a summary and conclusion. So, we need an intelligent power grid. Why? Because after the penetration of renewable energy resources into the power distribution grid, the traditional power grid cannot handle the power flow using existing control mechanisms. There is 2 reasons for this. The first reason, in the traditional power grid, there is only one-way electricity flow as seen on the upper side of the figure. But after the penetration of these renewable energy resources in the grid, there is 2-way electricity flow. The second reason, these renewable energy resources are distributed to whole country, even in some cases whole continent. So also these resources sometimes on and sometimes off, depending on weather condition. These cause a distributed and scalable power grid. To control such a critical infrastructure, we need an intelligent power grid, so-called smart grid. Smart grid requires enormous amount of the communication-based intelligent electrical devices and applications. Also, it needs a reliable and secure communication, because the control mechanism of the smart grid relies on the accuracy and timeliness of the acquired information. The distributed and scalable nature of the smart grid enforces us to use public network, internet. So, because deploying a dedicated network for such a dispersed system is not cost-effective way for the utility companies. But using the public network for such a critical infrastructure could introduce new security and reliability risks. Particularly, the best effort delivery services provided by internet could cause severe problem in the power grid. Also, DDoS attacks can render many critical smart grid devices inaccessible, which cause catastrophic problem in the power grid. In the smart grid, the first constraint, the smart grid devices have limited resources in terms of computational power, memory, and bandwidth. Also, these constrained smart grid devices need to transmit their data to many receivers. In addition to these constraints, the smart grid application have stringent quality of service requirements. In my thesis, I focused two quality of service metrics, the latency and availability. Also, I use the availability and reliability interchangeably, because many of the smart grid organizations use these terms interchangeably. Also, we can add another metrics as a quality of service metrics, but the smart grid community focus on these two primary metrics. So, if we use the internet for such a critical infrastructure, we probably face many problems. And the first problem could be that the existing quality of service approach doesn't provide end-to-end quality of service guarantee, because these quality of service approach are configured in each autonomous system in different manner. A promising solution to address this issue would be the overlay network-based approach. But this approach also has some limitation, especially in the providing high availability. The second problem would be that the existing DDoS attack mitigation approach cannot be easily deployed on the constrained in smart grid devices. Also, to address this problem, the overlay-based DDoS attack mitigation approach would be a promising solution. Also, this approach has some limitation in the providing timelines. So, we need a platform which provides end-to-end quality of service guarantee, plus a proactive security against DDoS attacks for the smart grid. So this slide lists my all contribution and corresponding problems. I can divide my contribution into two parts. The first part is related to quality of service aware communication. The second part is related to DDoS mitigation. In the first part, the problem, the best effort delivery service provided by internet. And the contribution which addresses this problem is titled Robust Quality of Service Aware Communication over Public Network for the Smart Grid. So in the second part, I address three types of DDoS attacks. And the first type of the DDoS attacks, volume-based DDoS attacks. The second one, application and transport layer attack. And the third one, the internal DDoS attacks. Also, I have three mechanisms to address these three problems, three type of the attack. And the combination of all of my contributions build a platform which provides end-to-end quality of service guarantee and a proactive security against the DDoS attacks for the smart grid. So let me move on to the second part of my presentation. As I mentioned in the problem statement, the internet doesn't provide end-to-end quality of service guarantee for the smart grid applications. But smart grid applications need low latency and high availability. That means quality of service guarantee. So to provide such a quality of service guarantee in the internet, we need a mechanism, a platform which doesn't need any change in the existing structure of the internet. And for this purpose, the overlay-based approach could be a promising solution. Overlay-based architectures basically bypassing the degraded path using the other overlay nodes as a router to enhance the quality of service provisioning. But this approach, the overlay-based approach, the existing overlay-based approach, either unscalable or for the enhancement of the quality of service provisioning in only best effort manner. So to provide a quality of service aware communication in scalable manner, I offer headgrid. So headgrid, as seen also in the figure, it firstly cluster the smart grid devices depending on their autonomous system. After that, it selects the strongest node as a super node, and this super node builds a secondary layer, and these super nodes only probing their physically adjacent links. And by doing so, we have a monitoring scheme which doesn't cause any extensive message overhead. So, but if there is a failure or congestion in the underlay, how does the headcrit handle this problem? Headcrit, after it detects the failure or congestion, it simply redirect the traffic, as seen also in the figure, over the secondary layer, and using the source routing based quality of service routing mechanism. Also, to provide the high availability, especially for critical smart grid application, we have two additional mechanisms for the headcrit. The first one, altruistic flow allocation, we call it. And altruistic flow allocation, simply, as seen also in the figure, it resolves the higher quality path for high priority application. Higher quality, it reserves the higher quality path for high priority application. Sorry. And also we employ the compensative multipath routing mechanism for high critical application, only for high critical application, and it simply transmits the replicated data over the physically disjoint path. So to test our system's performance in terms of providing quality of service aware communication in a underlay failure case, we build a simulation, and in this simulation first we build an internet-like topology and a background traffic for the 1000 overlay nodes, and also we implement a failure scenario in this setup. In this failure scenario, a BGP router fails for 10 minutes. During that time, the underlay network doesn't redirect the traffic, and we test how the headcrit redirects this traffic efficiently. As seen also in the figure, headcrit achieves significantly higher quality of service satisfaction rate for each priority compared to TCP. Especially also as seen in the figure, for the high critical application, it achieves higher quality of service satisfaction rate thanks to CMR and AFA approach of the headcrit. So also in our simulation, we we see that headcrit and TCP cause similar message overhead, because TCP has a large header for the smart grid application with small payloads, but headcrit uses the UDP with small header. Also, it only probe the critical links in the underlay in the internet. So, as a conclusion, headcrit achieves above 98% quality of service satisfaction rate in case where a BGP router fails for 10 minutes. Also, it provides a robust communication for the smart grid, and it doesn't need a dedicated infrastructure. Also, it's scalable and lightweight mechanism. So, in my first contribution, I addressed the quality of service issue that I mentioned in the problem statement. Now I will focus the DDoS attack issue that I mentioned in the problem statement. The first type of the attack that I will focus in my second contribution, the volume-based DDoS attacks. These days we start to hear frequently the terabit DDoS attacks in the internet. And if we use such a critical infrastructure, if we use the internet for such a critical infrastructure, probably we start to hear much more often this kind of attacks. So to counter such a high volume attack, we need a proactive, preventive DDoS attack mitigation for these constrained TN smart grid devices. An overlay-based mechanism could be a promising solution for this, but also in the overlay-based approach, if one of the overlay node is under the attack, during that time, the devices using this overlay node for communication can be inaccessible. And it can be inaccessible for short time. But this short time could be tolerable for web application, but not for smart grid. So also we need to address this issue as well. So to address this whole issue, I propose, I call it simply SRCP, a secure and reliable communication protocol for smart grid. SRCP basically a peer-to-peer and it's a broker-based EPUB subsystem. I built the SRCP on the head grid net, so you can simply think the brokers here are the supernode of the head grid. Yes. SRCP simply provide a proactive DDoS attack defense by decoupling the communicating constrained smart grid devices with a strong broker layer. So, but in such a system, the publisher and subscriber IP addresses are secret, but the access brokers' IP addresses are public. So they are vulnerable to DDoS attacks. So to counter such a high volume attack in such a system, we have two additional mechanisms for the SRCP. The first mechanism, data spreading mechanism. This mechanism simply spread the whole data across the access broker, and the secret brokers reassemble this data and deliver to subscribers. And if some of the data drop because of the attack, the secret broker, using some acknowledgement mechanism, it recovered this data. So, but the acknowledgement mechanism caused high delay for smart grid application. So, to address this issue, I have another mechanism. I call it a multi-homing based fast recovery mechanism. In this mechanism, I have two assumptions. I should explain first them. The first assumption, each access broker with multiple network interfaces. And second assumption, the publishers know which network interface, which IP addresses belong to which access broker, but attacker doesn't know this. So now let me explain the mechanism. In this mechanism, publisher transmits the consecutive data package to the network interface of each access broker. And if one of the network interfaces, as seen also in the figure, is under the attack of any access broker, this access broker, after a very short time, it requests the drop data over the functional network interfaces. So to test our system performance in terms of throughput and latency during the attack time, we deploy our system on a real testbed called NorNet, similar to PlanetLab. Also, we compare our system with a reference system called Angelos system here, which use the data spreading mechanism in basic manner as well. In our experiment, we see that SRCP provide. Also we use the 90% throughput as a baseline for our real-time application. And in our experiment, we see that SRCP provide over the 90% throughput up to 35% failure of the broker. But the other system after the 7% after the 7% failure of the broker, the throughput goes down the baseline. So in the latency also we see the similar outperforming of our system. Also we accept the 300 millisecond RTT as a baseline in our for our real-time application, and we see in our experiments SRCP meet this latency requirement up to 45% failure of the brokers. So as a conclusion, SRCP addresses a 5 times larger volume-based attacks compared to the Angelo system. Also, it meets the latency requirement up to 45% failure of the broker. Also, it's a scalable mechanism because it uses a peer-to-peer broker-based structure. So, in my second contribution, I addressed the volume-based attack with the SRCP. But if an attacker combines the volume-based attack with application and transport layer DDoS attacks, SRCP cannot handle such a much more efficient attack. So to counter such attacks, we need a lightweight defense mechanism against the application and transport layer DDoS attacks in addition to SRCP. So after adding this mechanism to SRCP, I call it PHSS anymore, port hopping spread spectrum. In the PHSS, to prevent the transport and application layer attacks, I use the port hopping mechanism. A port hopping mechanism, as seen also in the figure, the server changing it is open port periodically over the time, depending on a predefined port number sequence. And each client knows this predefined port number sequence and transmit their data depending on these numbers. And by doing so, the server hides the open port number from the attackers. So, but in such a system, each client knows the port number sequence. I call it a secret. So we have a shared secret disclosure risk. So how can we mitigate this risk? To mitigate this risk, I propose port shuffling based containment mechanism. This mechanism simply it clusters all clients and send them new port number sequence. After that, some of the cluster could be still under the attack, and the containment mechanism again will recluster this cluster until quarantine the compromised client. So to check our system's performance, firstly we check whether the port hopping mechanism caused any throughput degradation in the system or not, and we didn't see any degradation in our system. So also we test our containment mechanism performance, and we see that our containment mechanism quarantine the compromised client in very short time, and during this time the availability doesn't drop under the 98%. Also, we compared our system existing containment mechanism, and when this mechanism quarantine the compromised client, the availability goes down 60%. Also, this difference seen in the figure. So, as a conclusion, PHSS a lightweight and strong defense mechanism against application and transport layer attacks. Also, our containment mechanism quarantine the compromised client in very short time. Also, over minimum loss of the availability. So, in my third contribution, there was a there was a shared secret disclosure risks, and we have a mitigation method for this. But is it possible to remove this risk totally? Yes, possible. But we need such kind of a port hopping mechanism which doesn't use shared secret or shared port number sequence. So for each client. So to address this issue, I propose MPTCP-H. Sorry. MPTCP-H actually is an extension on the multipath TCP, MPTCP. So in the MPTCP-H, the server established different MPTCP connection with each client firstly. After that, it established multiple subflow with each client, and each client renewing these keys, these subflows periodically over the random new ports. By doing so, as seen also in the figure, we have such kind of a port hopping mechanism which doesn't use a shared secret. So to test our system performance against the DOS attacks, we launched a DOS attack against a system using our proposal and the TCP, and we see in our evaluation over the 90, our system provide over the 90% availability during the attack, but TCP, the system using the TCP provide under the 50% availability during the attack. The only drawback our system is that our system cause additional message overhead compared to TCP. So as a conclusion, MPTCP-H is a DDoS attack resilient transport protocol for the specifically wide area measurement system, but can be adapted to many other systems. Also, it provides higher availability during the attack time compared to TCP. As a conclusion, the distributed and scalable nature of the smart grid enforces us to use the public network, internet. But using internet for such a critical infrastructure could introduce new reliability and security risks. And the best effort delivery services and the DDoS attacks can cause severe problem in the power network. So to address these issues, I have 4 contributions, and combination of all of my contribution build a platform which provide end-to-end quality of service guarantee plus a proactive security against the DDoS attacks for the smart grid. These are my publications, which are the result of my PhD. Thank you very much for listening.